Hello and welcome to another exciting topic in the world of dynamics. This one deals with our third way that we can identify a location of a particle at any point in time. We started with rectangular coordinates where I could just designate this little blue dot as an x and a y distance away from the axis. Then we moved on to normal and tangential and describing the particle in those terms. This one is cylindrical coordinates where we're going to define the radial direction and the transverse direction. If I wanted to, and I can actually see that the green line represents the path of the particle. I have some radial distance r, which goes from the origin out to the particle, and some theta, which is a rotation from, in this case, the positive x-axis out to that position. With that donation or designation, what I can have is a unit vector in the radial direction, which points outward from that particle or from the origin outward. And then 90 degrees to that, I would have another unit vector which is in my transverse, which is a u sub theta. So our u hat r is in the radial direction. And I should note that this is positive outward, positive as we move away from our origin. And our u hat theta is the transverse direction. And I should point out that that one is positive in the counterclockwise, our typical positive notation when it comes to angles. From that, I can determine what my position is for this particle. And the way I do that is I say I have an r, my radial arm vector is equal to the length of the vector times my unit vector in the radial direction. Box that as it's like an official equation, make it look a little cooler. And once we have position, what we've seen in this class over and over and over is I can take the derivative of position to get velocity. So for this velocity vector, if I take the derivative of my position vector with respect to time, it's equal to velocity, I can see that there is r times the unit vector. That means I'm going to have to use the product rule. So in essence, I end up with the derivative of the first, which is r dot times the second, which is my unit vector, plus the first, which is just my r, times the derivative of the second, and that's theta hat u theta hat. And basically the reason I can do that is because I know that the derivative of my radial vector with respect to time, my radial unit vector, is equal to theta hat, or my rate of change in the transverse direction, times the unit vector in the transverse direction. So hopefully that makes a little bit of sense. Put a little bubble around that to say where it all came from. That was the derivative of this guy, or that's how I got that anyways. So substituting in some terms, then I can say that my velocity vector is equal to r dot, my velocity in the r radial direction times u r hat, plus my velocity in the transverse direction times my unit vector in the transverse direction. And this is kind of the form that I like to leave it in. And I like to leave it in that form with this extra little bit where I'm going to say, I'm going to define my velocity in the r is equal to r dot, and my velocity in the theta is equal to r theta dot. So if it comes to solving problems in dynamics, in essence what I'm starting off with is trying to figure out what my r dot and my theta dot are. It's usually either given or I can find pretty easily, and I can just plug it in. I can take the derivative again to get to my acceleration equation. So my acceleration would be the second derivative of my position vector with respect to time, or the first derivative of velocity with respect to time. So if I look at this now, I'm taking the derivative of this guy up here, so I have to use the product rule once again, and what I would see is I have the derivative of r dot, which is r double dot, times the second u r hat, plus the first, which is r dot, times derivative of the second. Well, we already determined the derivative of that would be theta hat u hat, well, u hat theta. And then I would have the whole second term. Now there are three parts to that second term up here. Because there's three parts, I have to use the product rule in essence, well, 3 times. So I end up with this r dot theta dot, which is derivative of the first times the next two, plus I have my r, the derivative of my middle part of this bit was theta double dot, u theta hat, and then I have a minus r theta dot squared u r hat. So the only thing that might look a little unfamiliar is that last one, and just like before, it's basically a definition of our derivative of the unit vector in the transverse direction with respect to time, which is equal to negative theta hat ur hat, sorry, theta dot. Thetas and dots and hats, and oh my, a lot going on here. So as this does look a little bit congested, I'm going to do some refinement, and I'm going to come up with an acceleration by separating out my unit vector u, r, and u theta, and I end up with r double dot minus r theta dot squared, and those are my two terms in this radial direction. In the transverse direction, I have a 2r dot theta dot plus r theta double dot. That's in my transverse or theta direction. So just like I did with velocity, I think the easiest way to represent this is to say that my total acceleration will be the acceleration in the radial direction times my unit vector in the radial direction plus my acceleration in the transverse direction times my unit vector in the transverse direction. Because if I look at there now, that looks pretty easy, right? That's just makes sense too, I think, somewhat makes sense in my crazy brain. Where, just like before, if I'm going to plug and chug, my acceleration in the radial direction would be equal to this r double dot minus r theta dot squared, and my acceleration in the transverse direction would be 2r dot theta dot plus r theta double dot. So there is these dynamic problems that might look kind of complicated, and it seems like there's a lot going on. But really with dynamics, these are some of the more simple problems you can solve. Here's the strategy that I like to use when I'm solving these problems. The first thing that I'm gonna want to do is look at the problem statement, and I'm going to solve for my r dot, and my r double dot. So I can just, if my radial position is given as a function of time, I take the derivative once to get r dot, take the derivative again to get r double dot, right? Same thing with this transverse direction. So I end up with a theta dot, and a theta double dot. So what that means is if the problem has theta as a function of time, you're taking the derivative. Now there might be a time where it's giving you a theta dot. In that case, you integrate to get theta, and then take the derivative to get theta double dot. You know, whatever you're doing to get those in essence 6 variables. Now it's usually a function of time, and it's usually saying at time equals something, tell me the velocity and acceleration. That's the most common problem. If that's true, the next thing you'd want to do is plug in whatever time is given, because you might have your r dot, r double dot all as functions of time. If you want to know the velocity and acceleration at time equal 3 seconds or something like that, then you plug in 3. Lastly, what you want to do is, looking at what we have up above, I want to solve for this velocity in the radial direction, which is just my r dot, my velocity in my theta direction, which is just equal to r theta dot. When I have those two components of velocity, I can find my total velocity, which would be equal to the square root of the squares, which we've seen before, right? Same idea with acceleration. So acceleration in the radial direction is just r double dot minus r theta dot squared, and the acceleration in my transverse direction is 2r dot theta dot plus r theta double dot. And once I have both those, if I need to, I can find a total absolute acceleration of acceleration in the radial direction squared plus the acceleration in the transverse direction squared. So that's kind of how I do it. let's do a quick example to show how this goes, and you should be on your way. So for an example, let's say I have a particle and I'm given that the radius is a function of time, which looks like 2 times the cosine of t. With a problem like that, because I have this augmentation or augment of the cosine, I have to tell you if that's in degrees or radians, so you know what to put your calculator in, and this one's going to be in degrees. And my transverse direction is t over 2. So both are as a function of time. What I'm going to try and find is the magnitude of the velocity and acceleration. And you could also find the direction, I suppose, but it gets a little bit kooky. Like I said, the first step that I would do is I would find my r dot, and r double dot. Well, r is just equal to my 2 cosine t. It's given. R dot is the derivative of that, so that's minus 2 times sine t, and r double dot is derivative of that, which I get minus 2 times the cosine of t. Same idea with my thetas. Theta is equal to t over 2, or 1/2 t. So that means my theta dot would be equal to 1/2, and my theta double dot is equal to 0, meaning it has a constant velocity in that transverse direction. After I have those 3 things, I said the second step that I would do is plug in time. I'm going to do steps 2 and 3 in this case because that's how I did it in my notes, and otherwise I'll get totally lost. So at time equal 100, oh, I didn't even finish that, did I? Find the magnitude of velocity acceleration at time equal 100 seconds. It helps if I actually tell you what you're looking for. So at 100 seconds, then I can say my velocity in the radial direction. Well, we said that's just equal to r dot, and that's equal to minus 2 times the sine of 100. And if I do all that, I end up with minus 1.97 feet per second. My velocity in the transverse direction, we said, is equal to our r theta dot. So our r is 2 times cosine 100, and I'm going to multiply that times my theta dot, which I have 1/2. And if I do all that, I end up with, hopefully, minus 0.174 feet per second. So my overall magnitude of velocity then would be the square root of those squares. And to save time, I'll assume you can do that part. I have 1.98 feet per second. Same idea with acceleration. My acceleration in the radial direction, we defined it as being r double dot minus r theta dot squared. So my r double dot is minus 2 times the cosine of 100. And then I have that minus this r, which is 2 times cosine 100, times theta dot squared. Well, theta dot is just 1/2 squared. If I do all that, I end up with something like 0.434 feet per second squared. And my acceleration in the, thinking transverse, but really theta, that's what I meant to write, otherwise it looks like tangent. My theta, I said that was equal to my 2r dot theta dot plus r theta double dot. Plugging that in, then I have 2r dot is a negative 2 times the sine of 100. And then my theta dot is 1/2 plus my r is 2 times cosine 100 times theta double dot, which is 0. So actually that whole last term goes away, which is really nice. And I end up with minus 1.97 feet per second squared. So I can combine those two accelerations using Pythagorean theorem, and I get an overall magnitude of acceleration of 2.02 feet per second squared. So like I said, these problems can look intimidating, but if you work them out in their steps, just keep your dots and your thetas and your r's all consistent. It's basically more of a plug and chug process, which I know a lot of people seem to like. So I hope that was helpful, and I look forward to talking to you soon. Thanks.